Hello everyone, this is Md Rafiue Islam, graduate student of Arkansas State University. Today I am going to give a presentation on seismic site response analysis in Northeast Arkansas. This project was supervised by Dr. Jahid Hussain, Associate Professor of Civil Engineering. The main goal of this study is to perform the seismic hazard analysis as well as gather shear velocity profile, collect ball log data, develop delineated design response spectrum, and estimate seismic site coefficient. This is the flow diagram of research methodology, which records the data of shear velocity, routine geometrical properties, target motion, time series data, positioning of time series data, spectral matching of time series data with target ground motion. Table 1 shows the shear velocity profile of Harrisburg from down to bedrock, and table 2 shows the upper 30-meter shear velocity profile of same location, and figure 2 shows the dynamic site characterization testing location in northeast Arkansas. This is methodology section. There are three approaches are available in this study. Site response analysis approach were followed. Basic inputs are soil properties, input ground motion, time stories, simulation of wave propagation using site response analysis platform called DeepSoil 7.0. First one is collection of various soil properties. Shear velocity profile for Harrisburg was collected from case 1603, and as far as to guidelines, this site can be classified as site class D since its shear velocity lies between 600 to 1200 feet per second. Input ground motion time stories. The USGS Unified Hazard tool was used to perform deaggregation, and from the deaggregation we found the mean magnitude of earthquake was 7.5, and mean source to site distance was found 45.13 kilometers. Besides, uniform hazard spectrum was also chosen for site class A using the USGS Unified Hazard tool over the time period or return period of 1000 years, or the probability of incidence 5% in 50 years. Selection of ground motion. 12 ground motions were selected from the neural database, and for selecting the ground motion, Cox defined quantity thumbs are followed, and then spectral matching was performed for the scale ground motion, since the initially selected ground motions often differ from the design motions in terms of peak amplitude, response spectral ordinates. This was done by using Seismometer 2020 and earthquake software for adjusting earthquake accelerogram to the target response spectrum. This figure shows the summary of matched ground motions with target motions using the Seismometer 2020. Total 12 ground motions were selected and matched with the target ground motion. Simulation of wave propagation was performed using DeepSoil 7.0, where both equivalent linear analysis and non-linear analysis were performed, and delineated design spectrum was developed by taking weighted average of 50-50 of both equivalent linear and non-linear analysis result. This is the result section. This figure shows the difference between equivalent linear analysis and non-linear analysis method. Figure 5 shows the sample comparison between equivalent linear analysis and non-linear analysis for different types of input ground motion. One is for Cape Mendocino and another is for Chichi, Taiwan. And figure shows that the summary of response spectrum obtained from equivalent linear analysis and non-linear analysis. And from this figure, it can be concluded that there is a difference between equivalent linear analysis and non-linear analysis. And most of the cases, equivalent linear analysis gives higher response both at short period as well as at a long period compared to that of non-linear analysis. This is because a flat response at higher frequency can be produced. Besides using constant stiffness and damping toward the analysis, equivalent linear analysis may give higher response both at short period as well as long period. On the other hand, soil behavior can be predicted precisely using non-linear analysis method. This is the finally developed delineated design spectrum, which was developed by taking 50-50 weighted average of equivalent linear analysis and non-linear analysis. From the figure, it is found that from the 0.01 second to 0.244 seconds, there is reduction of 33% PGA compared to that of Astro General Guides, and the weighted side class remains between two-thirds and one of Astro General procedure response spectrum during the time period of 0.224 second to 0.34 second, and after 3.45 second, it exceeds the Astro General response spectrum. This is the summary section, and this study demonstrates the usefulness of performing site-specific ground motion response analysis over code-based design spectrum. And it has been found that the code-based design spectrum may lead to over-designing the short-period structure at significant cost and under-designing the long-period structure at significant risk. From this seismic site ground motion response analysis, uh, it has been found that there is a reduction in anticipated design force compared to that of ASTO for the short period of time. On the other hand, for the long period of time, site-specific ground motion response analysis may predict amplification of anticipated seismic design force compared to that of ASTO. That means this seismic site ground motion response analysis can uh, save significant amount of money while designing short period structures. Thank you all.